Good evening, dear students. Today we will start a new topic in mathematics called probability. And this is one of the very important topic. Several questions comes every year. Before I proceed further, could you please confirm couple of you that you are able to hear my voice very clearly and able to view the screen properly, dear students? Could you please confirm couple of you, dear students?
Yes, sir.
Yes, sir.
Okay, great. Thanks for your confirmation. Okay, and I also got few messages that you are able to hear me. That's it. Thank you. Now let's understand probability by means of couple of examples. We often hear statements like it is likely, to rain today, or a statement like that. I have a fair chance of passing, the examination, or there is an even chance that a coin will come up with heads. Okay, that means if you toss a coin, that whatever you will be going to get, it is, it is a head. That is, in each case, what about the statement I just said, dear students, is that in each case, our statement refers to a situation in which we are not certain of the outcome, right? But we express some degree of confidence that our prediction will be verified. For example, when I say, it is likely to rain today, that means what? You cannot guarantee that rain is going to happen, but that statement, express some degree of confidence that, our prediction that it is going to be rain is going to be correct. But we cannot make sure that it is definitely going to rain. Okay, the theory of probability provides a mathematical framework for such kind of assertions. Okay, now how we can study, how we can enter to this subject to study about this probability, and how we can make sure that this kind of incidents, whatever the statements I mentioned, is actually can be expressed in the framework of probability. So now let us define what is probability. Okay, so the first statement, what comes to our understanding, is that we need to have a very good understanding about the definition of probability. So definition of probability is very important to have. What is that? Probability is a way of expressing knowledge or belief that an event will occur or has occurred. For example, when we say that is one statement I mentioned, that it is likely to be rain today. Okay, when I say it is likely to be rain today, what does it mean? It means is that I have a belief, okay, or I have knowledge based on the other circumstantial incidents that it is going to be rain today. Okay, if the it is cloudy and then and the season is also rainy season, all these circumstances actually and allow me to make the statement with confidence that it is likely to be rain today. Okay, now what is that probability? Probability is a way of expressing knowledge or belief that an event will occur. What is that event? Event is that it is likely to be rain today. That is the event. Now in that event, how much probability is there? It is here purely a number. Dear students, after some time we will see the probability of an event is purely a number, and that number is in between 0 and 1. If the number is 1 or towards 1, near to 1, then you can say that event is going to happen. Or if the number, that probability number is near to 0, it is very less chance to happen. Okay, for example, if I say that during this COVID situation is that if I say that by tomorrow all the COVID cases will disappear, it is not going to happen. Okay, with no confidence I can say this statement, right? So what is the probability of that event is near to zero. Unless some miracle happens, it is not going to happen. Or if I say, tomorrow there will be a 100% increment of the COVID positive cases, that is also not going to happen. Okay, both are not going to happen. Now, if I say that there is a I am confident that tomorrow there will be a 2% increment of the COVID positive cases than today. That is likely to happen, and that probability, event of that probability, could be near to 1. So, in a very simple term, what I can say, dear students, probability, happens to an event. Okay, and probability of that event is purely a number between 0 and 1. So whatever the definition I said, it is a English statement, that is, probability is a way of expressing knowledge or belief that an event will occur or has occurred. That is the English statement. Now, what is the mathematical definition? Mathematically, what we can say, the probability of an event A is defined by PA. It is denoted by PA and defined by, the number of outcomes favorable to the event A divided by total number of possible outcomes. Let me explain you a little bit, dear students, here. Suppose, you are tossing a coin. Tossing a coin is an experiment. More specifically, it is a random experiment. I'll come to those topics, that why it is a random experiment. Now, outcome of those random experiments are called events. For example, you toss a coin, then what are the possible outcomes? You are either going to get a head or you are going to get a tail. So getting a head is an event, or getting a tail is an event. So now, if I define that event A is getting head, then what is the probability of that event? Is that number of favorable, a number of outcomes favorable to the event A. Now, if you see the in a coin, there is one head and the other side is tail. So number of favorable event in case of tossing a coin is 1. And what are the total number of possible outcomes? There are 2. It can be either head or tail. So the probability of getting a head should be 1 by 2. Let us understand. Let me place this from my study material, and let me explain you further. Let us consider the following 2 examples. The first example, let me tell you, and let me spend some time in explaining this, because once you have the fundamentals clear, then it is a very easy way of moving forward. So let us consider the following 2 examples. The first one, a coin is tossed. What is the probability that a head will occur? What I just said, but it is in written format. Here the event is occurrence of head once a coin is tossed. That is the event. Okay. So occurrence of head once a, let me underline, occurrence of head once a coin is tossed. We see total number of possible outcomes are 2, head or tail. And the number of outcome favorable to the event, that is getting occurring a head, is 1. So the required probability that a head will occur is 1 by 2. Now, in the similar manner, dear students, if we say what is the probability that a tail will occur, similar manner it will be 1 by 2. Why? Because the total number of possible outcomes are 2. Now, tail is number of favorable outcomes. In that case, it is tail is 1. So the required probability that a tail will occur is also 1 by 2. I hope you got it, dear students. So this is all about now this experiment of tossing a coin. Now let me take another example. Okay, that example is that is also a very classical example when we discuss about probability. That is called a die. Suppose a die is thrown. What is the probability that the number that occur that the number that comes up with the die is a multiple of 3? Let us understand this case, dear students. Okay, so what is the if you see in the bold color, that is the problem and a question actually. So what is the question? First let me tell you the statement. A die is thrown, right? Die is, it has 6 faces. One face marked with number 1, second face with 2 dots. Number 1 means 1 dot. Second phase there are 2 dots. Third phase there are 3 dots, like that. A die is thrown. What is the probability that the number that comes up with the die is a multiple of 3? Now here, what is the event? Dear students, by reading that statement, you need to find that what is the event here. Here the event is appearance of a number multiple of 3. That is the event when a die is thrown. Now we see what are the total number of outcomes. If you throw a die, out of these 6 faces, any face will come up. So there are total number of cases. In this case is total number of possible outcomes is actually 6. Correct, no? Because there are 6 faces, and once you throw a die, any of the 6 faces can come. So the total number of possible outcomes is 6. Now let's see what are the possible number of favorable outcomes. Okay, the number of favorable outcomes is a multiple of 3. What are the multiple of 3 numbers, dear students? Is it 1? The number between 1 and 6, that is multiple of 3, are 3 and 6. If you see 1, 2, 3, 4, 5, 6, if I write these numbers here, dear students, that 1, 2, 3, 4, 5 and 6. If you see out of these 6 numbers, 3 is a multiple of 3 and 6 is a multiple of 3. So total number of outcomes favorable to the event of our discussion, that is appearance of a number multiple of 3, is 2, 3 and 6. So the required probability is 2 by 6, that is 1 by 3. Now up to this statement, one thing you are pretty sure, that whatever the probability is, the probability should be always less than equal to 1. Why? If you look into the numerator and denominator, numerator cannot be more than denominator, right? For example, if I say, I toss a coin, okay, what is the probability that that a head will occur? Now total number of possible outcomes is 2. It is impossible that number of favorable outcome, that is getting head, is more than 2, 3. I cannot say this thing now. Can you say that you toss a coin and there are 2 heads coming? It is impossible. Or 3 heads coming? Impossible. There is only 1 head. So numerator cannot be greater than the denominator. At most numerator can be equal to the denominator. Okay, then we can say the probability of the event is actually less than equal to 1. This is one case. Another case is that that number cannot be 0 as well, because it is a ratio of 2 numbers. A ratio of 2 numbers cannot be 0 unless the numerator is 0. Okay, so it can be at most 0, if I correct my statement. So it can be at most 0, but it cannot be less than 0. It cannot be a negative number. So what we can say, dear students, from whatever I said, that Probability of any event A is a number between 0 and 1, including both the numbers 0 and 1, which means for any event A, its probability, that is denoted by PA, must satisfy that inequality that 0 less than equal to PA less than equal to 1. Correct, dear students? So what I said, that probability of any event A is a number between 0 and 1, okay, including both the numbers, which means for any event A, its probability PA must satisfy the following inequality, that is 0 less than equal to PA less than equal to 1. Few minutes back I said that probability of event A cannot be 0. It can be 0, but there is a very rare case. Let me give you an example where the probability of event can be 0. If I say, I throw a die, what is the probability that I get a face which is marked with 8? That is not possible. There is no such cases. There is no such face which is marked with 8 dots. So it is number of favorable cases, outcomes is 0, by total number of cases is 6. 0 by 6 is 0. So probability of an event can be equal to 0, but it cannot be less than 0. Correct, dear students? So that is also a very important information, that 0 less than equal to PA less than equal to 1. Correct, dear students? Great. Now, what we are going to discuss is that some terminologies, and those terminologies are extremely important, okay, and very, very important. And the first one is called a random experiment. Dear students, that we all aware of experiment that we do in our laboratory. We do experiments, right? Okay, so then why the word random is there? For example, if you are there in your chemistry laboratory and you are performing one titration, and when you make this experiment, what is the result you are going to get. It is to some extent certain, but you want to make sure that you are getting it. So those kind of experiment is not random. Let me give you another example, that experiment which are not random. Suppose I want to go to a particular place, that is a particular college. Your college I want to visit, for example. Okay, there are many college students here now taking this class. Suppose I specifically say that, okay, I want to visit that that Mysore college, for example. The moment I say that I want to visit that Mysore college, and I know exactly which college I am referring to, and I have visited there earlier, so it is quite certain that I will be reaching there. Right? So it doesn't qualify to an experiment also. But suppose I do not know exactly where exactly which place in Mysore that college is. I'm going for the first time. Then I can make some experiment, but with confidence I can say that, yeah, I will reach there. Maybe it will be a little late, but I will definitely reach there. Okay. Now, these are called experiments. Now let me come with the random experiment. Random experiment, you know what, dear students, that an experiment should qualify to a random experiment if there are two conditions are true. First condition is that experiment has more than one possible outcome. Okay, let me give you an example. Suppose you toss a coin. Tossing a coin is an experiment. And not only an experiment, it is a random experiment. Why Because the possible outcomes are more than one. That means either you can get a hit or you can get a tail. Correct? For example, what I said few minutes back, that I want to go to the Mysore college. There, I cannot say that, I started from Bangalore towards Mysore college and I reached, Chennai. It is impossible, right? So that experiment cannot be random. It is definite that I am reaching to Mysore. Correct? Now, in the similar manner, that if you see that another experiment, suppose you throw a die. If you throw a die, you know that there are more than one outcomes. In fact, there are six possible outcomes: 1, 2, 3, 4, 5, 6. So that is the first condition, that an experiment can qualify to be a random experiment if number one condition is that the experiment has more than one possible outcome. And what is the second condition? Second condition is that during the process of random experiment, it is not possible to predict exactly which outcome that will be. Okay. For example, when you toss a coin, now when the coin is in the air, going up or coming down before hitting the ground, you really cannot predict that exactly what output is going to come, unless it actually hits the ground and rest, settle down. So during the process of random experiment means what? When the coin is in the air, going up or coming down. That is the process of random experiment. That is the a process in which the random experiment is taking place. So let me write down these two conditions, dear students, and then I'll explain further about that random experiment. An experiment is said to be a random experiment when both the following conditions hold true. Number one condition, the experiment, has more than one possible outcome. And second one is that during the process of random experiment, it is not possible to predict exactly which outcome that will be. I give one example of tossing a coin. I give an example of throwing a die. Like that, there are many examples. Now let me give you an example that where it is not random. Okay, suppose you have a coin where both the sides you marked with, head. Possible. Suppose you get a coin where both the sides are head. There is no head and tail. Both are head. Now, if you toss that coin, always you will get head, na? So that means it is not more than one possible outcome. The first condition is not holding true. So you can directly say, no, that experiment is not a random experiment. So I repeat, if you toss a coin when both the sides has head or both the sides are tail, you cannot say that tossing of that coin is a random experiment, because it doesn't have more than one possible outcome. Similarly, suppose you have a hypothetical die in which all the faces are marked with one. Then if you throw that die 100 times, 1,000 times, millions times, you'll always get that one dot. So it doesn't have more than one possible outcomes. So it also doesn't qualify to be a random experiment. And second thing is that suppose you have a coin where there is a head and tail. Now if you toss that coin, then when the coin, as I said 2 times earlier, when the coin is in the air, you really cannot say when it actually hits the ground and settle down whether I am going to get a head or tail. You just predict. Okay, if it actually meets with your prediction, you say that, oh, okay, whatever I thought it is coming, otherwise it doesn't come. It generally happens in most of the sports, beginning of the sports, football, cricket, etc. Right? Cricket, when two teams actually, come for a match, then depending on which captain own the toss, they decide whether they want to, bat first or bowl first. Correct? Now, so I already explained you the example. Now let me put that from the study material, and let me explain you for the last time. For example, the experiment of tossing a coin, and observing the output, that is either head or tail, is a random experiment. Okay. Is a random experiment. It should be A. Is a random experiment. Why? Because both the following conditions hold true. Number one, the experiment has 2 possible outcomes, head or tail. And while tossing a coin, it is not possible to predict exactly whether a head or a tail is going to be the outcome. So that's why tossing a coin isn't qualified to be a random experiment. Okay. Now the next terminology, dear students, is about the sample space, outcome, and event. These are very important about sample space, outcome, and event to understand. Okay, so let's understand about sample space, outcome, and event. So these terminologies, if you know well, then you can actually, once you start solving problems, first you need to define that what are the, from where these terminologies is actually, being defined, and then it will be very easy for you to, solve that problem. For example, if I say that there is a die is thrown, what is the probability that it is a multiple of 2? First, you need to understand what is the experiment. In fact, random experiment, that is the throwing the die. Then you need to find what is the event. Okay. Then what is the sample space? Then what are the possible outcomes? What are the events? So these are the things, if you define properly, then solving problem will be simple. Now, first let's understand what is a sample space. Sample space is a set containing all the possible outcomes of a random experiment. For example, in the random experiment of throwing a die, the sample space is the set 1, 2, 3, 4, 5, 6. Isn't it? So what we understood, dear students, about the sample space? Let me show it here. So sample space is a set containing all the possible outcomes of a random experiment. For example, in the random experiment of throwing a die, the sample space is the set 1, 2, 3, 4, 5, 6. That is what is called a sample space. And the second terminology is that outcome. What is an outcome? An outcome is a possible result of a random experiment. Okay, means outcome is an element of the set of the sample space. In a set theoretic notation, what you can say, an outcome, is an element of the set of the sample space. Let me define this and then, explain you once more. So, as you see, that an outcome is a possible result of random experiment. Okay, means outcome is an element, of the set sample space. For example, I throw a die, and outcome is a face with marked with 2. Then 2 is an element of that sample space, which is a set containing 1, 2, 3, 4, 5, 6. So that is an outcome. Now, after understanding about the sample space and outcome, the next one is called event. Now, from a set theoretic notation, we can say an event is a subset of the set of sample space. So sample space is a set. Then you discuss is that after the sample space is the outcome. Outcome is an element of the sample space. And what is event? Event is a subset of that set sample space. Okay, let me first write it down. Then let me explain you in details. So dear students, an event is a subset of the set sample space. For example, in the experiment of throwing of a die and observing the number of dots in the top face of the die has the sample space, the set called 1, 2, 3, 4, 5, 6. Correct. Any element of this set, for example 4, is an outcome. Now, the event of getting a face with even number of dots is the set 2, 4, 6 is a subset of the set of sample space 1, 2, 3, 4, 5, 6. So what we understood, dear students, that outcome is an element. For example, in this case, it is 4. So suppose we have a a die and we are throwing it, and then the sample space is the set 1, 2, 3, 4, 5, 6. That is the sample space, as you see, dear students. Sample space is the set 1, 2, 3, 4, 5, 6. Any element of the set, for example, 4 is an outcome. Any element of this set, for example, 4 is an outcome. Now the event of getting a face with even number of dots, that actually a set, which is contains the element 2, 4, 6. But that set is a subset of the set 1, 2, 3, 4, 5, 6, which is the sample space. Now the event of getting a face with an even number of dots is the set 2, 4, 6, and it is a subset of the set of sample space. Correct, dear students? So this is all about sample space, outcome, and event. Very important terminologies. Now, what we need to focus on in the events, there are different types of events, and we are going to concentrate on understanding those different types of events, dear students. Okay. I hope it is absolutely clear whatever we have discussed so far. Now, the first, so let me go to the next page. It is better to explain into the next page. And first, let me tell you that what are the different types of events. And I'll give examples in each and every case. So, let us consider S be the sample space corresponding to a random experiment. You can assume that random experiment of throwing a die, or you can assume the random experiment of tossing a coin, okay, or any other. These two are very classical examples. Generally, in every probability class we discussed with we give examples from these two experiments, and both are random experiments, as I said earlier. So now let S be the sample space corresponding to a random experiment. Now we are going to define the following types of the events one by one. The first one is called that impossible event. Okay. As you hear the statement, dear students, impossible, you know what is impossible means? Impossible means which is, not going to happen, not possible. Opposite of possible is impossible, right? From the English dictionary. So impossible event is that the null set. If we have the sample space, as a set, let S be the sample space. Now, the null set is called an impossible event. In few minutes back, we discussed about what is an event. Event is a subset. Now, phi is also a subset of whom? Subset of the sample space. Event is a set, and it is actually a subset of the sample space. So impossible event is a set which is a null set phi, and obviously it is an subset of the the sample space. Now, how can an impossible event occur? What is an impossible event? Let me give an example. For example, in the experiment of throwing a die, if I call an event like occurrence of 7, that is impossible. Why? Because only there are 6 phases marked with 1, 2, 3, 4, 5, 6. So then how come I can get an 7? Impossible. So now if I need to mathematically express this as a set, then it should be null set. Because in the previous lessons, whatever we have done few minutes back, we understood that event means it is a set. Now, if I say an event something like this, that okay, occurrence of 7 when I'm throwing a die, obviously it is an impossible event. Now, what is a set theoretic notation? Set theoretic notation of that impossible event is a null set phi. And obviously, phi is a subset of 1, 2, 3, 4, 5, 6, that's it, containing the elements, the sample spaces containing the element 1, 2, 3, 4, 5, 6. And dear students, I hope it is very clear to you by now. The probability of an impossible event is 0. For example, what literally it means is that suppose I throw a die and I'm telling, hey, what is the probability of getting an occurrence of 7? without having knowledge of probability, apart from the basic definition of probability, and it varies from 0 to 1, including 0 and 1, you can say, sir, it is 0. How you can expect 7 when there are 6 marks? Correct. So that is what is an impossible event. I hope you got a very clear idea about impossible event. Now next one is exactly opposite to that impossible event, and that is called sure event. What is sure event? Let me tell you one example of a sure event before I proceed further. Suppose I toss a coin, and tossing a coin is a random experiment, and I'm telling you, dear students, my event is that either a head or a tail. Then you tell, sir, it's a 100% it will come, sir. So then the probability of this is that 1. Because if you toss a coin, either it has to be a head or it has to be a tail when it touches the ground and settle down. So now you are defining an event called I'm going to get either a head or a tail. So obviously it is a sure event. So now let's come to a formal definition of sure event. The set S is called the sure event. Means whenever in a set theoretic notation, if S is the sample space, and that S is called the sure event from the set theoretic notation. Now let's look at a practical example. For example, in the experiment of throwing a die, an event called occurrence of any natural number between 1 and 6 is a sure event. Why it is a sure event? Because when a die is thrown, numbers for appearance are 1, 2, 3, 4, 5, 6. And obviously you know that probability of an sure event is 1. As I said by means of the previous example, that tossing a coin and my event is that getting either a head or a tail, obviously it is 1 because number of favorable outcomes are 2 and divided by total number of outcomes is 2. 2 by 2 is 1. So probability of sure event is 1. Now, dear students, let's define the next a type of event that is called a simple or elementary event. Let me explain you about the simple or elementary event, and let me first place the study material, the portion of the study material, and then let me explain you. So what is a simple or elementary event? A subset of the set S containing exactly one element is called the simple or elementary event. That means event is a set, moreover is a subset of the sample space. Now if that set is a singleton set, that means set containing exactly one element, then we call the corresponding event is a simple or elementary event. So now let's come to the set theoretic notation and definition. A subset of the set S containing exactly one and only one element, exactly only one element. Okay, exactly one element is sufficient. We don't need to mention only. Exactly one element is called the simple or elementary event. For example, in the experiment of throwing a die, an event called occurrence of multiple of 4 is a single or elementary event because from the number 1 to 6, multiple of 4 is only one number, that is 4. Right? That is why it is an elementary event. But if I say my event is multiple of 2, then it is not an elementary event because multiple of 2, it contains the set 2, 4 and 6, which is not a singleton set. So that is not an elementary event. So I repeat, dear students, before I proceed to the next point, is that a subset of the set S containing exactly one element is called the simple or elementary events. For example, in the experiment of throwing a die, an event called occurrence of multiple of 4 is a simple or elementary event as the number of favorable case for this event is only one, that is occurrence of the number 4. As 4 is the only natural number between the natural numbers 1 to 6, which is a multiple of 4. That is why it qualifies to be a simple or elementary event. Next one, dear students, is called compound event. Okay, compound event, uh, if you recall your English class, dear students, you know simple statement, compound statement, okay, like this actually. You can make an analogy. Once you understood about the compound event, you already understood what is simple event, and now you will understand in another few minutes about the compound event. And then if you recall your English class about the simple statement, compound statement, whatever you have learned in your earlier classes, you will find yeah, it makes sense. So let's now discuss about what is compound event. A subset of the set S containing at least two elements is called the compound event. For example, that is a set theoretic notation. That means that compound event set should have number of elements more than one. It has to be at least two or more than two. Let's take an example. In the experiment of throwing a die, an event called occurrence of multiple of 3, that is a compound event. Why? As the number of favorable cases for this event are 2, that is occurrence of the number 3 and 6, as 3 and 6 are the exactly two natural numbers between the natural numbers 1 to 6, which are multiple of 3. So that qualifies to be a compound event, right? The next one, what we are going to discuss, dear students, is called the complementary event. Okay, so let me explain you what is meant by the complementary event. Let me first, place the material, and then we'll discuss about the complementary event. Okay, so complementary event happens for another event. So let me first bring that event. So what is that event? Let A be an event. Now the complement of the event A is denoted by A prime and is actually defined by A prime is equal to S minus A. That is the difference between the set S and A. That is the set theoretic notation. Let me give an example. In the experiment of throwing a die, let us define A be the event called occurrence of multiple of 3. If the moment we say this thing event A is the occurrence of multiple of 3, then what is the corresponding set? A should be equal to 3, 6. These are the two elements of A, multiple of 3. Now what is the complement of that set A? The complement of this event A, that is A prime, is the event occurring of not multiple of 3. So surely how we can get it? A prime is equal to S minus A. S is what? 1, 2, 3, 4, 5, 6 minus 3, 6. That is the element containing two elements 3 and 6. So what we get? 1, 2, 4, 5. So what we can say? The complement of the event A, where A is that occurrence of multiple of 3, then A prime should be the event denoting getting phase occurring, or we can say occurrence of 1 or 2 or 4 or 5. So for any event A, it is true that probability of A is equal to probability of A plus probability of A prime is equal to 1. Let me focus on this particular point here, students. Okay, how it is becoming 1. Let us take the example, whatever is mentioned here, that our event A is occurrence of multiple of 3. Then what is the probability of A? Probability of A is equal to number of elements in the set is 2, that is 2, divided by total number of elements in the sample space is 6, that is equal to 1 by 3. Now what is probability of A prime? Probability of A prime, that is A prime is having 4 elements, that is 1, 2, 4, 5, that is 4, divided by total number of elements in that sample space is 6, so 4 by 6. 4 by 6 is nothing but 2 by 3. Now, dear students, if you add these two, this implies probability of A plus probability of A prime is equal to 1 by 3 plus 2 by 3. That is equal to what? 1. That's what we have claimed here. That probability of A plus probability of A prime is equal to 1. The complement of the event either denoted by A prime or as A bar, or sometime also it is denoted by A complement A. There is a C on right hand top corner of A. So this is known as the complementary event. Okay. Now the next point what I'm going to discuss, dear students, it is related to event, but that is called mutually exclusive event. Okay, so I want to discuss this thing in the next page. What is mutually exclusive event? So and as we are discussing about the set theoric notation, so I'll give you the example with a by means of Venn diagram. So think about, there is a sample space. Okay, so let me explain you about the sample space S, and in that sample space, what you are getting events E1, E2, E3 up to En. There are n events in that sample space. Okay, so if I give you a visual representation of this thing, so let me first explain you with a visual representation. Okay, suppose this is the sample space. In that sample space, dear students, there are events something like this. Let me use a different color. So there is the event something like this, then this, then we get this, these are the events. Suppose this is the event E1, this is the event E2, this is the event E3, this is the event E4, this is the event E5, and so on. It goes on like this. Means you can get that event something like this. So there is a property of these events. If you look into it, that that all these events, so if I go up to En, that the n events, that E1, E2, E3 up to En are n events. Now all these events are said to be mutually exclusive events if the following statement is true. That means if you take any two events, means they are sets, corresponding sets, their intersection is actually phi. That means there is no common element, right? And that is why we can write in the in the symbolic representation. Just a minute. So in symbolic representation, what we can say is that EI intersection EJ is equal to phi when I is not equal to j, obvious, because if I is equal to j, then their intersection cannot be phi, and ij from 1 to 3 up to n. Let's take an example. Okay. In the experiment of throwing a die, let E1 be the event getting an odd number. Okay. So getting an odd number and E2 be the event getting an even number. Sorry. Now, if E1 is the event getting an odd number, then what is the corresponding set? E1 should be 1, 3, 5, because these are the three numbers which are odd number between the natural number 1 to 6. And what is the event E2? That is 2, 4, 6, because E2 stands for the event getting an even number, and between 1 to 6 there are three even numbers, 2, 4 and 6. So what we see, we see that E1 intersection E2 is equal to 5. Correct? There is no common element between 1, 2, 1, 3, 5 and 2, 4, 6. So we see the events E1 and E2 are mutually exclusive event. Okay. So in relation to the probability, we can say these two events are mutually exclusive events. But when we say about their set theoric notation at the level of discussion about the abstraction of the set, then what we can say, EI and EJ are pairwise disjoint set. When you can say they are pairwise disjoint set, because when there is no common element between them. So this is what is known as the mutually exclusive events. This is very important type of events because there are a lot of problems we will see that where you need to study with the mutually exclusive event, and I'll explain you. But before that, I'd like to tell you another event that is called exhaustive event. You know, so exhaustive events is something like this. Let me first write down the statement and then I'll explain you about the exhaustive events. Then I'll explain you about the exhaustive events. Now, to understand exhaustive events, let us consider there are n events E1, E2, E3 up to En. These are the n events. Now, all these events are said to be exhaustive events if we make an union of all these events, you will get the set, that sample space, entire sample space. Okay, that means what? It is not possible to find any other event, okay, so that the element of that event, is not belongs to any of this E1, E2 up to En. So how we can make a symbolic representation of this? So let me show you, dear students, so that you get a fair amount of idea. Suppose this is a sample space, entire sample space, dear students. Okay, and on that we are going to define that different events. So this is one event, this is one event, this is one event, this is another event, this is another event, this is event, and this is event. For example, if you see, if I name these events as E1, E2, E3, E4, E5, E6, E7, and E8, what you see, dear students? If you make an union of all these sets, E1, E2, E3 up to E7, what we are going to get? We are going to get the entire sample space, yes. And that is what is called exhaustive events. Let me give an example. In the experiment of throwing a die, let E1 be the event getting an odd number and E2 be the event getting an even number. Then what is their corresponding set theoric notation? E1 should be the set 1, 3, 5. E1 should be the set 1, 3, 5. And E2 should be the set 2, 4, 6. So we see that E1 in union E2, U1 union E2 is equal to S, that is the entire sample space. Where the set S represents the sample space in the experiment of throwing a die. So we see that the event E1 and E2 are exhaustive events. Now, why I'm discussing these two events, one is mutually exclusive and exhaustive. Mutually exclusive and exhaustive. So we discussed about two things. One is that mutually exclusive events, and next one we discussed about the exhaustive events. Now we want to bring all these two together, that is mutually exclusive and exhaustive. And we'll see this is very important topic, and lot of cases are there. Probability examples are there where you need to apply this. Okay, so we are going to discuss about the mutually exclusive and exhaustive events. Okay, so let E1, E2, E3 up to En be n events of a sample space S. Now, all these n events are said to be mutually exclusive and exhaustive if following conditions hold true. That is, E1 intersection Ej is equal to phi when I is not equal to j, and Ij is belongs to 1 to up to n, that first n natural numbers. So that one, what I just tick mark, related to the mutually exclusive definition. And the second one, which I'm going to mark now, that is U1 union E2 and union E3 up to union En, that is equal to S. That leads from the exhaustive events. When these two are come together, then we called this set of events E1, E2, E3 up to En are both mutually exclusive and exhaustive. Okay. We will discuss later, dear students, about that there are practical examples, of events where they are both mutually exclusive and exhaustive at the same time. Okay, let me give you a very practical example. Suppose, a doctor visits his chamber. Doctor starts from his home and visits his chamber. Okay, and while I'm explaining, let me also, give a set theoric notation so that you can get a very clear idea about that what I'm talking about. Suppose this is the entire sample space, and in this sample space, doctor here we are discussing is that doctor is visiting from his home to his chamber. Okay, means to his hospital or clinic, whatever. And it has been always observed that whenever the doctor is actually coming to reaching to his clinic, he is almost delayed. If he is supposed to come at 5 o'clock in the evening, he is coming later than 5 o'clock. And it has been observed that if the doctor is coming by car, okay, there is a probability that he is getting late, so he is coming by car. If the doctor is coming by what is called bike, okay, there is a probability of that he is late. If the doctor is coming by auto, okay, there is a probability of getting late. If the doctor is coming by walking, there is a this is walking, probability of getting late. So let me write it down here is that this is walking. Okay, and suppose it is by cycle. Okay, now if you see, all these events are actually, these sets are mutually exclusive, because when the doctor is coming by car, he cannot come by auto at the same time. Correct? That's why it is mutually exclusive. And why it is exhaustive? Because finally doctor is coming, and he is coming by means of any of this commute, either car or bike or auto or cycle, or by walking, whatever. So this is a practical example of actually that where you need to study with mutually exclusiveness and exhaustiveness. Now, whatever the example we are discussing about the throwing of a die, let's see from that one. For example, let me write down this step first, and then you'll understand that very literally about that about mutually exclusive and exhaustive events. Okay, so here it is, dear students. Okay, for example, let us consider the random experiment, okay, of rolling a die. We see here the sample space is S. What is that? 1, 2, 3 up to 6. That is a sample space S. Let us now define the three events as below. The event A is a die top face and even number. That should be what? 246. Event B is that die top face is an odd number. That will be what? 135. And event C is that die top face is a number 10. Then what will it be? It will be 5 because there is no such face called 10 when you have a die marking from 1 to 6. So now these are the set A, 246, set B containing the elements 1, 3, 5, and set C is a null set. Now if you see that A intersection B, it is 5, B intersection C, it is 5, and C intersection, it is 5. So A intersection B, B intersection C, C intersection C, C intersection A is a 5. And if you make together that A union B union C, that is S. The first one, what I am marking in the blue color, that relates to the mutually exclusiveness. And the second one, what I'm marking in the green color, that relates to the exhaustiveness. So what we see, dear students, as it is satisfied by both the mutually exclusiveness and exhaustiveness, we can say the events, the three events ABC, are mutually exclusive and exhaustive at the same time. So we can say these three events ABC are mutually exclusive and exhaustive events. Correct, dear students? So we have a very clear idea about mutually exclusiveness and exhaustiveness. So dear students, with this note, I would like to conclude the class here today. In the next class, we will discuss about the set theoretic principles of probability and the other relevant topics. Okay. With this note, let me conclude the class. If you have any specific question, you can ask me. Otherwise, thank you very much, and we will have our class day after tomorrow, same time. Thank you.
Thank you, sir.
Thank you.